The derivative and tangent line problem. In 2.1, you are going to learn the derivative and tangent line problem. Recall from geometry, you can see this circle with two lines. One of them is called the tangent line. Another one is called the secant line. So let's recall what the tangent line was. Tangent line is the line that meets with a circle at exactly one point. And the secant line, we gotta first remember a chord. A chord of a circle is this segment whose endpoints lie on the circle, and a secant line of a circle would be a line that contains the chord. So easy way of describing secant line would be a line that contains exactly 2 points of a circle. In calculus, we identify the slope of the tangent line with the instantaneous rate of change of a function. So you can look at the first picture below. I have a function that is the shape of a parabola. And if I want to know what is the rate of change of this parabola at this point, you could find the tangent line at that point and get the slope of this tangent line. Then it will actually give you the rate of change at this particular x of this function. The slope of a tangent line, as they change along a curve, are the values of a new function called the derivative. So derivative is a slope function of a function. Or you could also think that the derivative is the function that calculates the instantaneous rate of change of a function. So as you see this first picture again, slope of this tangent line is obviously negative since the line is going down from left to right. So at this particular x on this parabola, the instantaneous rate of change is negative. Look at the next graph. Now, the tangent line at this particular x that looks like a vertex of this parabola is horizontal line. And you know horizontal line has a slope 0. So at this particular x, the instantaneous rate of change of this function is 0 because the slope of tangent line at this x is 0. Look at the third picture. The slope of this tangent line at this particular x is positive since the line is going up from left to right. So therefore, at this particular x on this parabola or this function, the instantaneous rate of change is positive. So now, how can we come up with a function that would calculate the instantaneous rate of change at each point of a function? You can see on curve, rate of change of the function changes. It's not the same. So look at this picture. There's a lot of line, but you can pay attention to the first one that has the largest slope, which is this one right here. And this will be then a secant line of this function because it meets with the function at exactly 2 points. So let's say this first point at x is x. So then y value, you're going to plug that x to your function f. So y value will be f of x. And let's say you went delta x amount to the right. So that next x value here will be x plus the delta x. Then point on this function f will be x plus delta x, comma, f of x plus delta x. Yes? Then we can actually calculate slope of this secant line using slope formula. And slope formula was rise over run. And rise is y direction, which is y2 minus y1 over run is x direction, which is x2 minus x1. So our slope was calculated in algebra class, y2 minus y1 over x2 minus x1. Again, go back to the picture. Here's my x1, y1. Here's your x2, y2. And let's plug in right here. And y2 is f of x plus delta x minus y1 is f of x right now. x2 is x plus delta x minus x1 is just x. So on the numerator, I cannot simplify, but on the denominator, x subtract x is 0. So I will just get f of x plus delta x minus f of x over delta x would give me the slope of the secant line. So the m secant is what we just said one more time. Slope of secant line is f of x plus delta x minus f of x over delta x. But wait a minute. I thought we want to find the slope of tangent line, not slope of a secant line. That's right. So now imagine you are making delta x smaller. So now let's say your x plus delta x was over here. So then now this become your second secant line. But try harder and make delta x even smaller. So that now this is your third secant line. But imagine you make it delta x smaller, smaller, smaller. And how smaller? You make delta x approaches to 0. So let's say one of the point is here and your next point is right here. But if delta x approaches 0, your points on x and x plus delta x will be almost coincide on top of each other, and eventually you will achieve the tangent line. We did learn the limit from chapter 1, and this is the reason why. So that we can come up with the derivative function. We can come up with a slope function. We can come up with instantaneous rate of change of a function. So as delta x approaches to 0, secant line gets closer and closer to becoming the tangent line. So slope of a tangent line can be achieved by limit of slope of secant line, which was f of x plus delta x minus f of x over delta x as delta x approaches to 0. And we call this derivative of a function f, denoted by f prime of x. Definition of derivative, f prime of x. The derivative of f at any x is given by f prime of x equal limit f of quantity x plus delta x minus f of x all over delta x as delta x approaches to 0. Example, find the derivative of f of x equal square root of quantity x minus 3. So given a function f of x, let's find the f prime function. All you have to do is really use this definition above and apply the limit as we learned in chapter 1. So let's go ahead and find the f prime of x function. So my f prime of x is equal to limit delta x approaches to 0, f of quantity x plus delta x minus f of x over delta x. Always start by writing the definition so that you don't get confused, which is equal to limit delta x approaches to 0. And now, if you go back to your function, my f of input is square root of input subtract 3. So my f of x plus delta x, now your input is x plus delta x. So when you apply that to this function above, square root of input subtract 3, and your input is x plus delta x, so it will be square root of x plus delta x subtract 3 minus f of x. You can just copy the f of x above, which is a square root of x minus 3 over delta x. Okay, so now to find the limit of this, if I do the direct substitution of 0 for the delta x, I get square root of x minus 3 minus square root of x minus 3 over 0. So I get 0 over 0. So I need to use the special technique that we learned in chapter 1, which is multiplied by quantity 1 that has a conjugate of a radical expression. So conjugate of square root of x plus delta x minus 3 minus square root of x minus 3 is square root of x plus delta x minus 3 plus square root of x minus 3. And I would have same expression in the denominator so that this fraction would have a value 1, which is equal to limit delta x approaches to 0. And my numerator is a minus b times a plus b, which is a squared minus b squared. So that would be square root square, which will get rid of the square root. So I will have x plus delta x minus 3 minus square of square root of x minus 3 will give me x minus 3. But because I'm subtracting, I need to put a parenthesis there so that I am subtracting the whole x minus 3. And denominator, I have a product now, and my product is delta x times square root of x plus delta x minus 3 plus square root of x minus 3. When you distribute the negative, x minus the x will be 0, and minus 3, when you distribute the negative, this will become plus 3. So negative 3 plus 3 will be also 0. So all you will have is really limit delta x approaches to 0 of delta x over delta x times square root of x plus delta x minus 3 plus square root of x minus 3. So now that you have a product over product, you could also cancel the delta x. So I would end up with limit delta x approaches to 0 of, when delta x and delta x cancel out, what do you have on the numerator? Yes, you would have 1 on the numerator. So it's a 1 over square root of x plus delta x minus 3 plus square root of x minus 3. So now you can plug 0 for delta x. So go ahead and do so to find the limit, and your limit would be 1 over radical x minus 3 plus radical x minus 3, which is 1 over 2 radical x minus 3. And thus, your f prime of x function is 1 over 2 radical x minus 3. Now, let's look at some notations for derivative. Given y equal f of x, we use f prime of x for derivative. We already saw that. And because y is f of x, we sometimes use y prime for f prime of x. That's understood, right? And next two notations are useful when we use different variables or if we have more than two variables. So you can see fraction notation, which you have a dy over dx, and that is actually read the derivative of y with respect to x. So here with respect to x, you know you are taking derivative of this function y with respect to the x variable. And also, because y is f of x, instead of y, you could actually put a f of x in there. And when we read that, we actually read it as the derivative with respect to x of f of x. Example, given that y equal 5 over x, find the derivative of y with respect to x. But you can just say dy dx, and we will understand that would be the derivative of y with respect to x. So let's find dy dx using definition of derivative as we just learned. So dy dx is equal to limit delta x approaches to 0 of f of x plus delta x minus f of x over delta x. That was the definition we just learned, right? So now apply my new input x plus delta x to my function y. Y is your f of x. My function rule is whatever the input is, do 5 over input. So now that tells me limit delta x approaches to 0. So f of x plus delta x, since my input is x plus delta x, f of x plus delta x is 5 over input, which is x plus delta x, minus f of x, you can just copy 5 over x, over delta x. And again, if you were to do the direct substitution, 0 for delta x, you can see that I get 5 over x minus 5 over x on the numerator, which is 0 over 0. Direct substitution wouldn't work here again. So we need to use special technique we learned in chapter 1 again. And what I have in here is complex fraction. So we are going to multiply by a quotient of value 1 whose numerator is the LCD of these denominators, x times quantity x plus delta x, over the same expression, x times quantity x plus delta x. And when you distribute this quantity to the first fraction, 5 over x plus delta x, x plus delta x, x plus delta x will cancel, and you will have 5 times x only, which is the 5x. So 5 times x, we end up getting 5x as the first term. Now, when you distribute this LCD to the second fraction, the factor x and x will cancel, and you will have minus 5 times x plus delta x. And denominator, I have a delta x times quantity x plus delta x. So that will all be in the product. Delta x times quantity x plus delta x. Now limit delta x approaches to 0. I'm going to distribute -5 to both the terms inside of a parenthesis. And you can see that when I distribute the first time, 5x minus 5x will be 0. So all I'm gonna get is -5 times the delta x, which is -5 times delta x over delta x times quantity x plus delta x. We have now product over product in our quotient. So we can again cancel the delta x. So I have limit delta x approaches to 0 of -5 over x times quantity x plus delta x. So go ahead and do the direct substitution of 0 for delta x. Will give me -5 over x times x. So finally, my limit is equal to -5 over x squared. So my derivative of y with respect to x is equal to -5 over x squared. Slope of the tangent line is given by the derivative. So we learned that the derivative function is a slope function. It will calculate the slope of a tangent line at any point. And it is written by a function. We call it f prime of x. So once you have that function, you can actually calculate the slope of a tangent line at any x point you want. All you have to do is get the slope function and plug x equal the value that you want the slope of a tangent line at. So m tangent, which means the slope of a tangent line, is equal to f prime of x, and that was limit delta x approaches to 0 of f of quantity x plus delta x minus f of x all over delta x. So now once you have that, you can actually calculate specific slope at a specific x value by plugging x equal a into your f prime function. So m tangent slash at x equal a is equal to f prime of a, and it will give you a number, and that will be the slope of a tangent line at x equal a. So now you have the slope, and because you know where you want the slope at, you can find the equation of the tangent line. So recall from algebra, if you have a point and a slope, we could write the equation of a line using point-slope form of a line. And point-slope form of a line was y minus y1 equal m parentheses x minus x1. And from there, if problem asks you to give the answer in slope-intercept form, you can distribute the slope m and add y1 both sides to isolate y. You will have y equal mx plus b. If a problem asks you to give the standard form of a line, then you would distribute the m and then have x and y term on the left-hand side and have the constant term on the right-hand side. All right, so let's do a specific example. Find the equation of the line that is tangent to f of x equal x cubed minus 2x at the point 2, 4. So all I need is really to find the slope m. And to do that, we're going to find the derivative function, which is f prime function. And then we're going to plug x equal 2 there to calculate the slope at x equal 2. All right, so let's find the slope function m tangent, which is equal to our f prime of x. And we can find the f prime of x using limit definition. And that is limit delta x approaches to 0 of f of quantity x plus delta x minus f of x over delta x, which is equal to limit delta x approaches to 0. And now my function f of x is whatever the input is, I need to do the input cube minus 2 times the input. Since my input is x plus delta x, you need to do input x plus delta x input cube minus 2 times input x plus delta x minus f of x. And because my fx is more than one term and because I'm subtracting, I need to make sure to put the parentheses there. Remember me telling you that before? And now my f of x, you can just copy, and it is x cubed minus 2x there over delta x. All right, now you could either use Pascal's triangle, or you could use binomial theorem, or you could memorize how you could expand a plus b to the third power. But I'm going to use Pascal's triangle really quick. So that will be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. I think we learned this from quick algebra review. So this was a plus b to the 0th power. This was a plus b to the 4th power. This is a plus b to the 2nd power. This is a plus b to the 3rd power, and it is coefficient of your variable. So when you multiply x plus delta x to the 3rd power, what you're gonna get is, on the 4th term, you're gonna get 1 times x to the 3rd power plus, next coefficient will be 3 times, and you're gonna lose 1 power of that and gain 1 power of the next term. So it will be 3x squared delta x. This is the next coefficient of your binomial expansion. So that's a 3 times. You're gonna lose again an x, but now you're gonna gain one more factor of delta x. So that will be 3x times delta x squared. Last coefficient of binomial expansion is 1. You're gonna lose x, so there will be no more x term, and you will have all delta x to the 3rd power. And you're gonna distribute the negative 2 to both the terms inside of a parenthesis, which is negative 2x minus 2 times the delta x. I'm going to distribute this negative 2, both the terms inside of a parenthesis. Let me erase Pascal's triangle here now. So when you distribute this negative now, I will get minus x cubed plus 2x over delta x. And I'm hoping some terms would disappear. X cubed minus x cubed disappear. Minus 2x plus 2x disappear. So what's left is 3x squared delta x plus 3x delta x squared plus delta x cubed minus 2 times the delta x over delta x. So if I were to do the direct substitution now for 0 for delta x, since every term has a delta x in it, I will get 0 on the numerator, I will get 0 in the denominator. So that's no good. And the special technique we learned from chapter 1 in this case was, hopefully we can factor out the common factor that will cancel, so therefore we could substitute 0 for delta x at the end to calculate the limit. So we are going to factor out the delta x from the numerator, and that is delta x approaches to 0. And if you factor out the delta x from the numerator, from the 4th term, you took it out delta x, so you have a 3x squared. From the 2nd term, you took it out one of the delta x factors, so you have 3x, but you still have one more delta x factor. And from 3rd one, you had a delta x factor, 3 of them, But because you took one of them out, you will still have delta x squared there. And from last one, when you take the delta x out, you get negative 2 over delta x, which is ideal for what we have right now. So delta x and delta x will cancel. I only have a numerator. Now you get to substitute 0 for delta x. So this term will become 0. When you plug 0 for delta x, this term will become 0. So all you have left is really 3x squared minus 2. So I found my f prime of x. My derivative function, slope function, is 3x squared minus 2. With this now, I can find the slope of a tangent line at any x I want. But I want slope of a tangent line especially at this point 2, 4. So m slope at x equal 2 is f prime of 2. So plug 2 in your f prime function that you found. So that will be 3 times 2 squared minus 2, which is 2 squared is 4. 4 times 3 is 12 minus 2, which is 10. So slope is 10. And I have a point 2, 4 here. So using slope 10 and 2, 4 to find the equation of a tangent line, first we will use a point slope form of a line. So we will use that. This point is your x1, y1. Now, my point slope form of a line is y minus y1, which is 4, equal m, I just found it is 10, parenthesis, x minus x1, my x1 is 2. But they said write the answer in slope-intercept form. So I need to distribute the 10 and move negative 4 to the other hand side. So I have a y minus 4 equal 10x minus 20. When I add for both sides, I get y equal 10x. When you add 4, negative 20 plus 4 is minus 16. So I found the equation of tangent line in slope-intercept form. Alternate form of derivative. Alternate form of derivative calculates slope at specific point right away without getting slope function. Idea is that if you look at this secant line, first point is c comma f of c, and the next point could be any random x comma f of x. So if I were to find slope of a tangent line at c comma f of c, do the same strategy how we get the slope function. So slope of this secant line is right now f of x minus f of c over x minus c, right? But I want slope of a tangent line at specific x equals c. So all you really have to do is send x to c, right? So it will give me tangent line there. This is where alternate form of derivative came from. It's actually faster way of getting the slope if you are only gonna need slope of a tangent line at just one point. If you need the multiple points, then it's better to have a slope function and just plug different x value in there. But if you're only gonna get one of them, might as well just get it right away. So f prime of c is equal to what we just found here, slope of secant line here, but you send the x to c instead. Given f of x equal x squared plus x minus 2 at the point 2, 4, find the slope of the tangent line at P. You're going to have to eventually memorize the formula up there. We want slope at x equal 2. So this will be slope at x equal 2. And you can get that by right away using the formula above. That will be f prime of 2. And that will be limit Right now our c is 2. So x approaches to 2 of f of x minus f of 2 over x minus 2. So every c you see in the formula, you're going to have to plug x equal 2 in there, which is equal to limit x approaches to 2 of fx. You just copy. Here's a f of x. So you plug x squared. So you replace f of x by x squared plus x minus 2 minus. I need to find the f of 2, but f of 2 is right here. So this is f of 2. So f of 2 is 4 x minus 2 equal limit x approaches to of x squared plus x. Negative 2 minus 4 is minus 6 over x minus 2. Now, direct substitution won't work because I see already my denominator will become 0, and that will be undefined. So special technique we learned in this case was, yes, factoring the numerator. And hopefully it will have x minus 2 factor, and x minus 2 factors should be canceled, so I could do the direct substitution afterwards. How does x squared plus x minus 6 factor? You think of two numbers whose product is negative 6 and sum is a positive 1. What are those two numbers? Yes, that will be plus 3 minus 2 over x minus 2. Yay! It does have x minus 2 factors up and bottom, so we can cancel them. Now you get to do the direct substitution, and you can see that limit will be 2 plus 3, which is equal to 5. So you found the slope of a tangent line at x equal 2. Give the equation of the tangent line and put answer in slope-intercept form. Okay, so now I have a point 2, 4, and your slope, you found it, and it is 5. So point slope form of a line was y minus y1 equal m parenthesis x minus x1. So I have y minus 4 equal slope 5 parenthesis x minus 2. Now when you distribute the 5, you get y minus 4 equal 5x minus 10. You can move the negative 4 to the other hand side, and your equation of the tangent line in slope-intercept form is y equal 5x minus 6. Next, it says, plot the graph of f and the tangent line. So my original function is fx equal x squared plus x minus 2. I can find the vertex. Do you remember how to find the vertex of a parabola? It is negative b over 2a, comma, f of negative b over 2a. So negative 1 over 2 times my a is 1. So that's a negative 1/2. And my y value of a vertex is f of negative 1/2 is equal to negative 1/2 square plus negative 1/2 minus 2, which is equal to 1/4 minus half minus 2, which is equal to, you can get the common denominator 4. And if a common denominator is 4, you get 1 there, times 2, you get negative 2, times 4, you get negative 8. So you get negative 9/4. So I found the vertex is negative 1/2, comma, negative 9 over 4 is about negative 2 1/4. So your vertex will be, it will be about here. And that function, x squared plus x minus 2, 8 factors, so I could also find the x-intercept. This function, two numbers whose product is -2, sum is +1 is +2 and -1. So my two x-intercept is -2 and a +1. And because they gave me 0.2, 4 on my parabola, my graph should look like that. And my tangent line is y = 5x - 6. So it has y-intercept -6. And slope is 5, which is rise 5, run 1, rise 5, run 1. So this is my tangent line. So I graphed my function and a tangent line at 2, 4.